Welcome to our first lecture, actually, first part of our lecture about multimedia networks. In this lecture, we'll learn about networking, that essentially basically general networking, and then the areas and the technologies within the networking area and field that deals with special cases of multimedia delivery. And digital games are no exception in the case of specialized networking technology. So first, let me talk a little bit about what digital networks and communication had been in the past, and the changes that appeared in multimedia and networking technologies that brought us to digital networks. After the invention of telephone, there was an easy way, actually. It was possible for people from different areas to be able to establish an analog connection over some lines carrying electricity that would encode and represent their voices with electrical signals and essentially electrical charge. And at the receiving end, you would be able to decode that electrical signal into voice. And that was the basis of voice band communications. Basically, the idea in voice band communication is that you would establish a connection by closing a circuit using a circuit switching technique, and then you would be able to transmit electrical signal and information over the line, over the circuit. This way of communication allows the two ends of the connection to transmit over 3,000 kilohertz, or essentially 3,000 repetitions of the electrical signal per second. So that's the baseline of the bandwidth. The advantages of this way of communication is that you can create real-time connections between a sender and a receiver. There is very low latency, which means that once someone speaks, with very little delay time, the other person will be able to receive the sound signal. And essentially, because the signal, electrical signal, is transmitted in the form of an electromagnetic energy and wave, it travels at the speed of light. And there's a very high reliability in the connection and the communication. But the problem with this way of communication is that it can be only used for low-band signals. And human voice, especially, is a special kinds of signal that its majority of energy is contained within a very small energy band. And the bandwidth is essentially 4 kilohertz. And since you can transmit and receive signals with up to 3 kilohertz of frequency, and this can easily use human voice to encode it, because it's a low band signal, and transmit it. And there's very little information loss in that sense. So it's a really good voice-based communication system. There are several problems with this circuit switching technology and technique, and that is, one of them is that it cannot be used to transmit multimedia information. And the reason for that is basically its low bandwidth. And since it has very low band, it can only transmit very low frequency signals and multimedia signals, and multimedia applications inherently require high frequency of communication. Another special disadvantage of circuit switching technology is that only the two ends of connection that have acquired a dedicated actual physical circuit by applying the switches will be able to transmit signals. So inherently, the number of senders and receivers using this technology will be very limited. In contrast to the analog telephone services, there are digital networks. And in the early 50s, I believe, the MIT research labs started looking into the idea of creating a packet switching network as opposed to a circuit switching network. And I'll talk about that a little bit and the differences. With the packet switching technology, you do not have to have a actual dedicated line between the receiver and sender, but rather the receiver and sender could acquire intermittently the possession of a shared line, and then over the time that they have the possession of the line, they would send their information within packets. And this way, many number of different individuals and senders as well as receivers can be able to be connected at the same time. And also that releases the low band criteria over your signals, because um, depending on the way that you dissect your signal into smaller packets, you can have different kinds of bandwidths. This idea was developed as a part of PhD dissertations of several people, including Evan Sutherland, Bob Taylor, Lawrence Roberts, and Leonard Kleinrock in MIT Media Lab. And based off of this packet switching technology, Department of Defense created a large-scale development of a project that was called ARPANET, or Advanced Research Projects Agency Network, and that was the basis of the development of the Internet. By 1964, the Department of Defense's Advanced Research Project Agency network was established. 4 nodes were created that had dedicated leased phone lines. The laboratories at University of California at Los Angeles, University of California at Santa Barbara, Stanford Research Institute, and University of Utah were the first 4 nodes for this network. And the messages and signals were transmitted and received by a tool that was called Interface Message Processor. And you can see an example, a picture of one of the Interface Research Processors, essentially an IMP, which were the world's first routers that were utilized within that network. This project basically was commenced and finalized by 1969, and essentially was overshadowed by the first landing of human on the moon, Neil Armstrong, in the same year. And that was such a great achievement for the mankind that year that almost any other news was completely overshadowed by the fact that the United States achieved the first place in the space race by placing a live human on the moon and returning them back to the Earth. And by the way, Neil Armstrong, the first man on the moon, passed away yesterday. So that is a bittersweet story at the moment. And that same year, 1969, was the year of the creation of the ARPANET, which is the parent of the Internet as we know it. The ARPANET grew over the year, and in the early 70s, there were several incremental developments for the ARPANET, and so the network grew in size. 3 years later, there were 3 institutions in the United States that were connected via this ARPANET, and the first email was developed so that the researchers within those institutions that were sharing the network were able to send and receive messages, digital messages. There were several application protocols that were developed during that time. One of the most widely known protocols, called File Transfer Protocol, or FTP, is the protocol that we are still using today when we are sharing files over the Internet. Telnet was a network that was a network protocol that was created for telephony networks. There was the development of Simple Mail Transfer Protocol, or SMTP, and that is the protocol that you all are using when you're sending an email and when you're basically essentially reading your emails from the USB mail servers. There was one big problem with this massive and rapid development of the network. This was an explosive growth for one single network to be sustainable. Now, if we look at the Internet and want to see how this development essentially took place over the history of the digital networking and digital media. Here's a simple chart, a simple table that highlights the development of the internet. 1970 was the year that the internet had 13 hosts, and the first cross-country link was also installed by AT&T to connect networks across the country. So that was when the ARPANET essentially used the network backbone of the digital communication companies in the US. And the hosts increased to 35 in 3 years, and ARPANET became an international network. It expanded to University College in London, England, and the Royal Radar Establishment of Norway. In 1984, there were about over 1,000 internet hosts. ARPANET was divided into 2 subnetworks: Milnet for military needs and ARPANET for research. In the next few years, the number of hosts essentially increased by 1,000% actually, and the ARPANET project was basically concluded officially, and the internet was turned over to the public. And there was the Internet Society that was established to manage the internet. Just in 1 year, the number of hosts doubled. An association was established to allow businesses to be able to connect and use the internet. And in over 3 years, the network was basically well into having over 1 million hosts. And that was when the first web browser was created by Tim Berners-Lee, a British scientist who was working at the time at the European Research Center for Nuclear Research, CERN. And the first web browser that was created by Tim Berners-Lee is basically called Mosaic, and it was released to the internet users to basically allow them to surf the contents of the internet in a very seamless and fluent and fluid way. And that basically exploded the internet to what we have it now. Now, when we're looking at the internet, or basically any kind of connection between different devices, we would have to break it down into a layered architecture. And that is to allow one end of this communication, receiver or the sender, to be able to use its own processing and computational power to send and receive messages to almost any other kind of computational platform. So when you look at that, one of the most advanced and probably used architectures that's out there is the OSI architecture. It's a 7-layer architecture that allows 2 different devices of different sizes, different computational power, and even different hardware to be able to connect to each other over the network. The highest level, or the highest layer in this connection, or in this layered architecture, is in the application layer. The application layer basically is what you see, for example, when you open up an email, when you open up a web browser, and when you open your SMS messaging technology, or MMS messaging technology rather, on your cell phone. The application layer basically talks to your hardware architecture directly with your hardware architecture languages, which is your operating system in a sense. And it breaks down the communication and gives it back to a presentation layer. The presentation layer will break down this message essentially into a subset or subcomponents that contains the content of the message, as well as the information about the sender and receiver of the message, which is passed through the session transport layers down to the network layer. The network layer is responsible for breaking the sender and receiver information packets further down to create the actual physical locations or addresses of this information to be sent to. That is passed through the data link, and that data link layer breaks that down into actual 0 and 1s to transmit over a physical medium, which could be either a wired connection, such as a LAN, or a telephone wired, or a wireless connection, like Wi-Fi. And the physical layer basically is responsible for transmitting this 0 and 1 information from one location to the next. Each of these information packets will be sent through the physical layer, and if needed, goes through a router. Router shares the last 3 layers of your OSI architecture, namely the network, the data, and the physical layers, and passes these packets of information to the next router and the next router until it reaches the destination. The first 4 layers, or the highest 4 layers, are also called the peer-to-peer layers. And if your devices are sharing essentially the connection in a peer-to-peer network, which means that they can speak directly to each other, the network and the information does not need to be broken down and passed through the network, data link, and physical layer. So all this information over the peer-to-peer network connections can also happen at the lowest level on the transport layer.